Okay, this is a video for the honors geometry assignment, which I just extended the deadline on because I think I need a better explanation for this year's course. So Euclid's second proposition is about the following situation. We have a segment AB and another point C. And the challenge is, can we make another segment off of C that connects to some other point that is the exact same length as AB? And more so than that, can we prove with only the things we've learned so far in class that it is the same length as AB? So we can't measure it. We have to use circles and triangles and things like that to prove that we can do this. So I'm going to go through the construction here. It's fairly complicated, but then we'll look at it and write down the steps as to why it must be the case that we can in fact do that with only the things we've learned about so far in class. So first, I'm going to add a segment from A to C. And then from the A to C, I'm going to construct an equilateral triangle the way we've learned in class. And then I'm going to add a point right here. All right. And then I'm going to add a few more circles. One circle centered at, oh, sorry, I'm going to add in these segments for the triangle. Then I'm going to add a circle centered at A with radius AB. Then a circle, of course I need some rays, getting ahead of myself, at D through A and at D through C. And then I need one more circle at D through, oh, before I can do that, whoops, I need to add points, point here. And my circle is to go from D through to point E. Okay. And then I add one more point, and then my construction is done. And I'm going to move some points around a little bit, so this is just a little nicer to look at. There, that's nice. So I'm going to take a screenshot of this. And we're going to explain why this works. All right. So our argument here, our goal, is to show that AB, the segment AB, is in fact equivalent to the length of segment CF. Because CF is the thing we made that should be the same exact length as AB. And that was the goal, to show that if we have a segment and another point, yes, we can make another segment with the exact same length. So we're now going to go through the steps you would have to use to show that and write them all out. So we've got a 2-column proof, statements and reasons. So there's the statement first that AB is the same as segment, same length as segment AE. Okay. That should be pretty clear why. They are both the radius of circle A. Circle A. Okay. These two, I'm gonna kind of shade them in. These two have now been shown to be the same length. Okay. What else do we know to be true? Well, we constructed this equilateral triangle. So we know that AD and AC and CA are all the same. But for the purposes of this, all we really need to do, well, let's just say that. We'll say that this triangle ADC is equilateral. How do we know it's equilateral? Well, we used Euclid's first proposition before last week. Now we can state it as a reason because we proved that it works. Euclid's first proposition. So once we prove something in math, we get to use that in other proofs. And we'll see that throughout the year. Once we prove something, we can then use it for other things. So because ADC is equilateral, we can now say that DA is the same length as DC. Why is that? Definition of equilateral triangle. Okay. Right. So now those are all the same. All right, now I'm going to argue that DE is the same length as DF. Okay, why would that be true? DE is the same as DF. Well, DE and DF, those are both radii of circle D. All right. Okay, the next step is to say that we can now say that AE is the same length as CF. The reason here is a little tricky. It's because DE is the same as DF, but they both contain parts of this equilateral triangle which are known to be equal. So if we removed DA and DC from their respective segments, the remaining segments AE and CF would be the same length. So really we're saying we have two things that are long but equal. We take away an equal small part, the remaining part will be equal. So what we're going to state here for the reason is the subtraction property of equality. Now only one last step to say, which is now we can finish the proof and say that AB equals CF. And this is true because of the transitive property. Why the transitive property? Well, if AE equals CF and AB equals AE, then AB must equal CF. So that's the transitive property. Two different things are equal to AE, so these two things must equal each other. That is that AB here was shown to be equal to AE, and CF here was shown to be equal to AE. If they're both equal to AE, they are equal to each other. That's the transitive property. Again, transitive property is really simple, so it's kind of hard to explain it because explaining simple things is hard.